Okay, this is A.B.F.3, Algebra, Building, New Functions, Standard 3, Video 1, Graphing, y is equal to ax squared plus c. A few terms to know. I'd like you to copy these down in your journals and define them. All right, we are going to start with the most basic quadratic function in the family of quadratic functions, and we call this the parent. We have done this already earlier in the year when we were dealing with the linear functions and the parent. So the only difference today is that we have our x raised to the second power. So the exponent has now changed in our graphing, and we're going to see what happens to these lines as we change the exponent in the original equation. I think we dealt with y is equal to mx before, and that ended up just being y is equal to x to the first power. So what happens today when x changes to the second power? I've created a function table here on the right, and we are going to grab input values for x. I'll start right in the middle at 0, and let's square that. So if x is equal to 0 and I square it, that's 0 times 0. We are at the origin. A lot of our talk today is going to begin with this parent, and most of the time it will be starting at the origin, and then we'll talk about the adjustments that occur from there. Choose another random value. I'm going to stick to the pretty basic ones of, what do we have, 1 and -1, and then we have 2 and -2, 3 and -3, and we'll stop there for now. We could keep going 4 or -4. But what's going to happen mathematically in our table, if I take our x to be 1 and I square it, well, 1 times 1 is 1, 2 squared is 4, 3 squared is 9, I'll do one more down here, 4 squared is 16, and then going upwards, -1 squared, I want to actually write this out for you. So it's the quantity of -1 squared. So that's -1 times -1 gets us a +1. Then we have +4. -3 times -3 is +9. -4 again would be +16. So just imagine that that's in there, because I think on the next page I've graphed all the way from -4 to +4. All right, so this is the parent. This is the look of the parent quadratic function at y is equal to x squared. I'm going to freehand the parabola today. I was looking for a function on here. I wasn't able to find it, and I'm just going to do my best. And you're going to have to do your best when you're assessed on this at drawing this parabola freehanded. All right, so we have our 0, 0, the 1, 1, the 2, 4, the 3, 9, and the 4, 16. And then the other side of the parabola were our negatives. So we went -1, 1, -2, 4. We went x was -3, and we got 9. And then x was -4, and we ended up with +16. So the look of this, pretty close. And that would be the parent. Put some arrows on the ends because it continues. The parent function looks as you see it here in red. That is the red function called y equals x squared. And all of our talks in this video are going to be compared to this particular picture. And if you're looking at this red parabola right now, I like to compare it to it being the x-axis that was kind of bent. You know, so here is a straight line, a linear function at the beginning of the year that bent tremendously. It's aiming upwards towards the air, towards the sky, not the air, towards the sky. And that is what this little exponent 2 did to our linear function. We are now quadratic. All right, so the rest of our discussion is going to be manipulating that equation of y is equal to x squared. As you see on the lower left here in red, I have changed the x squared into an ax squared. So that is the coefficient. Now this coefficient can be many different types of numbers. In this particular example, we are only going to deal with a coefficient that is greater than 0. All right, what are all of the numbers that are greater than 0? Well, we have fractions, and we have whole numbers, and we have mixed numbers. As long as they are greater than 0, they are going to fall into one of these two categories over here on the right. All right, so let's first, since we're comparing to the parent, why don't I quickly try to get that parabola up there that is known as y is equal to x squared. All right, so what did we have? We had a 0, 0, we had a 1, 1, we had a 2, 4, we had a 3, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we had a 4, 16, 1, 2, 3, 4. This was 9, 10, 11, 12, 13, 14, 15, 16. And in your terms, we have something called the axis of symmetry. Symmetry, it's going to be the same on the other side. So right now, the y-axis is acting as our axis of symmetry. It is cutting the parabola in half. So I'm just going to count the distances away from the y-axis and plot them on the other side. So we were 1 over, we go 1 to the left. We were 2 over, we go 2 to the left. 3 to the left. 1, 2, 3, 4, 1, 2, 3, 4. Thank you to the axis of symmetry. We have just graphed the parent equation again. I'll do my best here. Put the arrows. Okay. Now let's take each one of these. This is going to be a vertical shrink. If I have, let me drag this up top here. If I have an A value, that would be this value, this value right here. If A, the coefficient, is between 0 and 1. So if I'm between 0 and 1, that would be all of the decimals or fractions. And we could start listing some of these decimals and fractions as being, oh, I don't know, famous one is 1/2. Maybe we have 1/4 is A, 1/3. We could go 2/5. We could make A anything we want. If it's a fraction or a decimal and it's less than 1, got to be less than 1, we have what we call a vertical shrink. Now, I don't have any examples in here. We're going to do the examples in class. The look of the shrink, if you're taking your eye on this red parent parabola and shrinking it, you're actually bending it down towards the original x-axis. So it is shrinking back to its 0. All right, so let's see if I could draw a green line in there. And I'm just going to make one up and try to be pretty consistent here. So it's going to be wider than the parent. And the fraction, depending on what fraction it is, will tell you how wide that green bowl is actually going to look. All right, so we call that a vertical shrink. Now, if A is greater than 1, that means 2, 3, 4, 5, maybe the mixed numbers, 1.5, 2.5, 2 3/4. Anything greater than 1, we are going to have this parent stretch. And if you think about stretching, when you're tired, you're reaching towards the sky when you're tired and you're stretching. So we're going to take this red parent and stretch it even further. And I'll just try to make one up here. And we are on the inside of the parent. I should have put some arrows there too. Okay, and the number, the integer that is aiming at the A, the larger that number is, the more stretched or the more thin that parent is going to become. All right, the next screen, we now are talking about what happens to our A if it is less than 0. All right, so what numbers are less than 0? You're talking about your negatives. Now there's a difference between your negatives. We have negatives that are fractions between -1 and 0 like we had on the last screen, and we have negatives that are completely less than -1. So those are going to be your negative mixed numbers, less than -1. All right, so we start with the parent, and let me see if I can, how much of this do we really need? Let me slide this down a little so we can see what the parent is. There's our origin, 1, 1, 2, 4, 1, 2 over, 1 over, and I'm just going to estimate these, and we're going up, and we're going up. If I am looking at the green one now, a shrink is the same idea. It has to be a negative fraction. So we're looking at fractions such as A is equal to, I don't know, -1/2, maybe -3/4. And the negative tells you that we are going to be shrinking it. And I'm sorry, no, the negative is telling us to reflect it over the x-axis, and then the fraction tells me to shrink it. So it's going to actually look, a little bit wider than the original parent. I know this is probably getting confusing. It's a lot easier with you in class. So this is for your study purposes, and then when we get into class, it's going to be a lot easier for me to explain to you in person. So let's just keep going with this format here. So we take the parent, we reflect it over the x-axis. Let me get my green pen out to kind of stay consistent here. And then it is going to be a shrink, so it's going to get wider. All right, so there's your reflection and there's your shrink. The negative is the reflection. The shrink makes it get wide. And then if I'm looking at the blue one here, a stretch with a reflection, that means we have a reflection of the red going over the x-axis and then becoming thinner than the original parent. So see how wide this parent is? We're going to go inside of that. Okay. The last part, now it looks like we are going to keep the parent the same, and the only difference is that we're going to take the parent and we are either going to move it vertically upward or downward on the y-axis. And what tells us about that? Well, the C value, the C over here, tells us if we're going to start this parent on the positive side of the x-axis or on the negative side of the x-axis. We're just going to be shifting it, translating it up or down. All right, so again, we're going to start with the old parent function. 1, 1, 2, 1, 2, 3, 4, 1, 2, 3, 5, 6, 7, 8, 9. Oh, wait. 5, 6, 7, 8, 9. 1, 2, 3, 1, 2, 3. There's our axis of symmetry again. 1, 2, 3. 1, 2, 1, 1. All right, there is the parent. Let's see how that works. All right, so keeping the parent the same, the C is going to tell us if C is positive 1, we're just going to take the parent and we're going to move it to the plus 1 on the y-axis. If it was at plus 4, we're not going to alter the look of the parent. We're just going to start the parent on positive 4. And the same idea, if it was at a negative 2, we would start at the 0 and then drop it down to showing us the vertical translation on the y-axis. And I think that would wrap it up. Here's some terminology that we have discussed earlier in the year. I'd like you to use the same terminology. We just finished with the vertical translation upward or downward on the y-axis. We've discussed the vertical stretch, and by a factor of, well, a factor of means what is that coefficient that we used. Stretch has to be greater than 1, so maybe it was by a scale factor of 3. Maybe it was y is equal to 3x squared. How about the vertical shrink? Well, the vertical shrink was that widening of the parent. It got closer to the x-axis. It was straightening out. And an example of that might be, how about y is equal to 1/4 x squared. And then we dealt with the reflection, and that was the parent that was mirrored or reflected over the x-axis, and that was when we dealt with the negative. So if the parent is equal to x squared, then the reflection of the parent is the negative x squared parent. And again, that number in front, that coefficient could be it could be any of the examples above. Maybe we have y is equal to negative 3x squared. So that would be a reflection over the x-axis, and then a what? That would be a stretch, a vertical stretch by a scale factor of 3, positive 3. So the reflection is the negative and the scale factor of positive 3. We will talk about that in class. Very, very intense topic with a lot of wording, a lot of ideas. So this is going to take us a little while before we get into graphing trinomials. That's going to be a lot of fun later on. All right, in your journal, I'd like you to define the given terms on page 2 of the flip chart. Write a few sentences on what you learned from this video. Maybe watch it over again. Try to get some of the wording down, and have a pretty good idea when you get back to class of some of these topics and some of these different looks of this new equation or this new function. See you in class.